Hello, welcome back. Let us go with the next design problem. The problem goes like this. Design an RC column, having unsupported length having unsupported length 2.75 meter to support a load of 2000 kilonewton using M20 concrete and Fe 415 steel. See, so the problem says design an RC column having unsupported length 2.75 meter to support a load of 2000 kilonewton using M20 concrete and Fe 415 steel. See, this problem does not give any cross-sectional dimension. That means we can give whatever section convenient for us, and also we need to find out how much reinforcement is required. And also it gives the total unsupported length of the column as 2.75 meter. It does not give any effective length, and also it does not give any end conditions. So in such case, what we can do is we can assume the end conditions as suitable for us. Okay, so let us take this. So given unsupported length is 2.75 meter, and the load given, that is service load P equal to 2000 kilonewton. Therefore design load PU equal to 1.5 times the service load, that is 2000, that is equal to 3000 kilonewton. Okay, and we are using M20 concrete, therefore FCK equal to 20 Newton per millimeter square, and we are using Fe 415 steel, that's why Fy equal to 415 Newton per millimeter square, and unsupported length L equal to 2.75 meter. Okay, so by assuming both ends as hinged, LE, that is the effective length LE equal to K times L, where K equal to 1. So L is 2.75, that is equal to 2.75 meter is the effective length. So this is as per table 28, page 94 of the code book. So let us assume the column, that the column is short and E minimum is less than or at most equal to 0.05 D. Therefore, PU equal to 0.5 4 FCK AC plus 0.67 FY ASC. See, this is given on page 71 under 39.3. So to use this formula, so we have to satisfy two conditions. One is the column should be short, and the other is E minimum should be less than or at most equal to 0.05 D. So to make use of this formula, because I don't have the dimensions of the column, so I cannot find out whether the column is long or short, because I don't have the dimension. So if you want to check whether the column is long or short, LE divided by DRB I need. So I don't know that. So I cannot check whether the column is long or short. Similarly, to find out E minimum, I need L by 500 plus D by 30 as per 25.4 on page 42. Here I don't know this, DRB. So I don't know this or this. So I cannot find out what is E minimum. So in the absence of the dimensions of the column, so I cannot find out these two values. However, I am using this formula assuming these two conditions are satisfied. So once I have this, I am going to find out what are the dimensions required for the column. Then I go back and satisfy these two conditions later. Okay. So coming back to this, in this equation PU is known, FCK is 20, M20 concrete. So AC is area of concrete, that is given by gross area of cross section minus area of compression steel plus 0.67 FY ASC, that is the area of compression steel. Okay. Here we have two unknowns. This we don't know and this we don't know. But we have only one equation. So by having one equation, we cannot solve for two unknowns. So in this case, what we have to do is we have to assume one of the values. The code says minimum reinforcement we have to provide for a column is 0.8% of the gross area, and maximum reinforcement we can go for is 6% of the gross area. So based on that, what I do is I am going to assume 2% of the gross area is the area of compression steel required. So let us assume the area of compression steel equal to 2% of the gross area of the column. 2% of the gross area of the column. That is 2 divided by 100 multiplied by Ag, that is equal to 0.02 Ag. Okay. So if I call this as equation 1, I am going to substitute this value in this equation. So that is Pu equal to 0.4 FCK, and AC is the area of concrete. If we have a column like this and with reinforcement, this is the plan I have written. So area of concrete is the gross sectional area minus the area of the steel. So that's why I am going to write here as AG minus AC, AG minus ASC, that is gross area minus the area of compression steel, plus 0.67 FYASC. Going further, Pu equal to 0.4 FCK and Ag, in place of ASC I am going to substitute 0.02 Ag, that is 0.02 Ag plus 0.67 into Fy, that is 415, and in place of ASC I am going to substitute 0.02 Ag. Here going further, that is PU is 3000 kilonewton. Convert the value into Newton, 0.4. FCK is M20 concrete multiplied by 0.98 Ag plus 0.67 into 415 into 0.02 Ag. Here Ag is the only unknown. Therefore, Ag equal to 223,864 millimeter square. That is the gross area of cross section of the column required. Here comes the question whether we have to provide a square column or a rectangular column. So in this problem, nothing is mentioned whether we have to provide a square column or the rectangular column. In this case, what is, for my convenience, I am going to go for a square column. So let us provide a square column. E minimum should not be less than 20 mm. What it means is, say this value instead of 21.33, say it is around 16 mm. So we have to take 20 mm as the minimum eccentricity. Okay. In general, take here of these two values as the minimum eccentricity. So going further, so therefore E minimum equal to 21.33 millimeter and 0.05 D equal to 0.05 into 475, that is 23.75 millimeter. Okay. Therefore, here E minimum is less than 0.05 D. Therefore, OK. What is the meaning of OK? So both conditions are satisfied. That is, the column is short and E minimum is less than 0.05 D. That way we are justified in making use of the formula given under 39.3 on page 71 of the code book. Okay. So once we have this, we have to go back and we have to find out what is the actual area of steel required using the same formula. Now we know the dimensions of this section, that is 475 by 475. To find out the actual area of steel, ASC, actual area of steel, ASC. So again we are going to make use of the same formula. We have PU equal to 0.4 FCK AC plus 0.67 FY ASC. So for PU I am going to substitute 3000 followed by 3 zeros because I am converting the values into Newton. 0.4 into 20. As far as area of concrete is concerned, that is Ag minus the area of compression steel. So what is the Ag value? That is the gross sectional area, that is 475 by 475 minus area of the compression steel will give you the area of concrete in the column plus 0.67 into Fy is 415 and ASC is the area of compression steel. Therefore, ASC equal to 4425 millimeter square. That is the area of compression steel required. Okay. Let us provide 28 mm dia bars. Therefore, number of bars equal to total area of steel required divided by area of each bar, that is equal to 7.19. So say 8. Okay. So once we provided 8 bars, therefore actual area of steel, ASC equal to 8 bars multiplied by pi by 4, 28 square. Okay. So that is 4926 millimeter square. 4926 millimeter square. That is the actual area of steel provided. So there is one more here. We don't know whether 28 millimeter diameter bars are existing in the market or not. If not, go for a different diameter of the bar, find out how many bars we need. Okay, then provide that many number. Okay, here I am assuming that 28 millimeter diameter bar is available in the market. So coming back to this, so once we have ASC 4926 millimeter square, percentage of compression steel provided equal to total area of steel and gross area of the column section multiplied by 100. That is equal to 2.17% is the actual percentage of steel we are providing. That is 2.18%, not 17, 2.18%. Okay. So this is greater than ASC minimum. That is equal to 0.8%. And again this is less than ASC maximum, that is equal to 6%. Therefore, okay. So here check for minimum reinforcement and maximum reinforcement. Both conditions are checked. So as per the code, the minimum steel we have to provide is 0.8%. In case if the design calculation requires less steel and if the steel provided goes below 0.8%, the code specifies provide at least 0.8% of the gross area. Okay. In this case, we have provided 2.18%, which is greater than 0.8%. So ASC minimum condition is satisfied. So what is the other condition? ASC maximum. That means we should not provide steel in the column greater than 6%. So 2.18% is less than 6%. This is also okay. What in case we get greater than 6% here? That means whatever sectional dimensions of the column we have provided is not adequate. So increase the sectional dimensions of the column and redesign. That is, find out what is the new area of compression steel required. So what are the new dimensions, and just basically you need to revise the design. Okay, here we are okay. Therefore, we shall provide 8 bars of 28 millimeter dia. Okay. So once this is done, the next problem is to provide lateral ties. That is lateral ties. So this is as per, of course, 26.5.3.2 on page 5.3.2c on page 49 of the code book. Okay, if you go there, 49, if you refer second column, it covers pitch and diameter of lateral ties. Okay, let us go with the dia of the lateral ties. The code says the dia should not be, that is, higher of the following two. The code says the dia should not be less than the following two. So one is 1/4 the dia of the largest bar. So here what is the largest bar? So we have only one size. So that is 28 millimeter. So that is the largest bar, and also that is the smallest bar. So 1/4 the dia of the largest bar is 1/4 of 28, that is equal to 7 millimeter. And also the code says the dia should not be less than 6 mm. That means provide the lateral ties of diameter which is at least higher of these two values. So of course we have to provide 7 millimeter diameter lateral ties, but 7 millimeter diameter lateral ties are not available in the market. So we go for a higher value, that is 8 millimeter diameter lateral ties. Therefore, we shall provide 8 mm dia lateral ties. Next comes the pitch or the spacing, that is the pitch of the lateral ties. So that is, the code says the pitch should not be greater than the following three. Okay, so one is least lateral dimension, of the column. Here the column dimension is, or the column dimensions are 475 by 475. So same size. So what is the least lateral dimension? That is 475. What is the largest lateral dimension? That is 475. So least lateral dimension in this case is 475 millimeter. And also the spacing should not be greater than 16 times the dia of the smallest bar. Smallest bar, that is equal to 16 times, what is the smallest bar? Again, only 28 mm dia bars we have. So we can take that as the smallest, that is 448 millimeter. Next, and the code says it should not be greater than 300, that is not greater than 300 millimeter. So whenever you provide lateral ties, the spacing should not exceed these three. That means we can provide lateral ties at a spacing of 300 millimeter center to center. That means take the least of these three values as the maximum spacing of lateral ties. Why we say maximum spacing? We can provide lateral ties at 300 millimeter center to center, not beyond that, not greater than that. But if you need, or if you want, we can reduce the spacing of lateral ties to say 275 millimeter center to center or 250 millimeter center to center. So here we are going to provide, therefore, we shall provide (8 mm) dia lateral ties at 300 millimeter center to center. Okay. This completes the design. After this is done, so the next thing is showing reinforcement details. So we are providing 8 bars, okay, and the lateral ties we are going to provide like this. Okay, and these are the main bars or longitudinal bars. And the lateral ties go like this. Okay. The dimensions of the column 475 millimeter by 475 millimeter. Okay, and these are main reinforcements. Eight of 28 millimeter diameter, so that is these bars, and this is the spacing or the pitch of the lateral ties. So 8 mm dia lateral ties or transverse reinforcement or transverse ties at 300 millimeter center to center. So same thing here. Okay. So this completes the problem. Of course, this is the plan and this is the sectional elevation. Okay, and the total length of the column is 2.75 meter, that is 2750 millimeter. Express everything in millimeter. Okay, is this clear to you? So this completes the design. Okay, I'm going to give some problems for you to practice at home. Please write down those problems. Those are examination problems. Design an RCC column to support an ultimate load of 1800 kilonewton. So effective length effective length 1.85 meter, M20 concrete, and Fe 415 steel. So of course this problem carried 10 marks. So let us go through the problem. Design an RCC column to support an ultimate load of 1800 kilonewton. So ultimate load is nothing but the design load, okay, or factored load. So you don't have to multiply this value by 1.5. That is already multiplied. So you take this load as PU. Okay. Next, effective length is 1.85 meter. So then what is the total length or unsupported length? Unless we know the end conditions, we cannot find out what is the unsupported length. So if this is effective length, by assuming both ends as hinged, the effective length will become the unsupported length. Where do you get the value? Go to table 28 on page 94. When both ends are hinged, then K value, that is effective length, equal to K multiplied by L, where K is the factor which is equal to 1 and L is the unsupported length. Okay. So that is L equal to 1.85 meter. Okay. So coming to this, the problem does not say it is a square column or a rectangular column. The choice is yours. You follow the same steps I did for the previous problem to solve this design. So we shall go with the next problem. Design a rectangular column subjected to an axial factored load of 1800 kilonewton. Take effective length equal to 3.2 meter. Use M20 concrete and Fe 415 steel full stop. Check for minimum eccentricity in the directions. So 10 marks. 10 marks. See, it is a rectangular column, it is not a square column. And PU load is given, factored load, that is 1800 kilonewton. So effective length 3.2 meter. Assume both ends as hinged, then this becomes the total length or the unsupported length. So use M20 concrete and Fe 415 steel. So check for minimum eccentricity in the directions. That means even without saying this, we are going to check. So here the problem is, it says rectangular section. So for example, if I take the previous problem which I solved, so we got the area equal to 223,864 millimeter square as the area. Okay. Because we decided to design that column as a square column, so we took the dimensions, or we found out the dimensions of the square that turned out to be 473 millimeter. That is, say 475 millimeter. Is it not? So we provided 475 by 475 square column. If you are providing a rectangular column, so don't change the calculation or the steps until you find out this. So go to a margin, find out what are the dimensions required for a square column, 473 by 473. Okay, because you are providing a rectangular column, so reduce one of the dimensions, because you are providing a rectangular column, say one of the dimensions is 400 millimeter. Okay. So the other dimension is given by this area 223,864 divided by 400, that is equal to 569 millimeter. So we are not going to provide 569, say 600. Okay. That means we are going to provide a rectangular column of dimensions 400 millimeter by 600 millimeter. You got it? So this is the way you are going to find out what are the dimensions required for a rectangular column. That is, find out the area by assuming certain percentage of steel. Okay, once you know the gross area of the section, just to get a glimpse of what dimensions required if you are to provide a square column, take the square root of it, you get some idea if it was a square 473 by 473. Because the problem says it should be a rectangular column, so reduce 473 below that value, say 400. So one dimension is fixed in a rectangular column. So total area divided by 400, we are going to get the other dimension of the rectangular column. So of course we are not going to provide this fractional value for a column. So we are going to go for higher value, which is 600 millimeter. Now we know the dimensions of the column. Then check for minimum eccentricity in both directions and also check whether the column is long or short. So after that is done, so make use of the same formula, Pu equal to 0.4 FCK AC plus 0.67 FI ASC, and by knowing this, find out the new area of steel, that is the actual area of compression steel required, and go ahead and provide any number of bars of the required diameter. Is it clear to you? So that is the way you are going to approach. Of course, you have to provide lateral ties. So let us write down the next problem. A 3 meter height column is effectively held in position at both ends and restrained against rotation at one end. Design the column to carry a factored axial load of 3000 kilonewton. Use M20 concrete. And Fe415 steel. Sketch the reinforcement details. Again, this question carried 10 marks. So the problem goes like this. A 3 meter height, that is the unsupported length of the column, is effectively held in position at both ends and restrained against rotation. So if you go to table number 28 on page 94 of the code book, for this end condition, that is one end is fixed and the other end is hinged. So you are going to get the value of K, that is the recommended value. Okay, refer that. So effective length will be equal to 0.80 times the unsupported length, which is equal to 3 meter in this problem. Is this clear to you? Okay, then go ahead and solve the problem. Here the column section you can provide as a square column or a rectangular column. The choice is left to you. The problem does not specifically mention the shape of the column. Is it clear to you? So go and practice these problems and you will be okay with the design of rectangular and square columns. Okay? Thank you.